Okay, now we're going to continue with chapter 12, part 2. These slides will be, there'll be a lot more applicable. We'll be seeing more math and physical relationships and applying it versus more of the theoretical that we just talked about. Okay, so let's get into it. Okay, solubility. So we can measure solubility, and we can measure it as the mass of the solute per 100 grams solvent. Okay, so that's a good way to compare it. If extra solute is added to saturated solution, extra solute will remain as a separate phase, and we'll be getting into this when we talk about equilibrium of solvation. And so, for instance, if you take salt and dissolve it in water and keep adding salt and water, there'll become a point where you add so much salt that it just won't dissolve anymore. And we would call that the saturation point. And we're not going to worry about that, but there is a upper limit to solubility of substances. Now, some of the effects on solubility. One of the things is temperature. You can change how well things dissolve in water, but one way to do that is by changing the temperature. Generally, substances become more soluble as you increase temperature. And what this does is it increases the disorder of both the solvent and solution, so they can mix better. Okay, so here's the diagram. Most substances become more soluble as temperature increases. You see that? So here's temperature and here's solubility. So as you increase temperature, solubility goes up. And you can see it varies considerably with each kind of substance, depending on the substance. Also, gases can be the solubility of gases change as well with temperature. Again, the solubility of gases usually decrease with temperature, so it's kind of the opposite. So what the last one is that if you want to increase the solubility of a solid, you can increase the temperature. But for gases, if you increase the temperature, you're actually going to decrease the solubility. And here's some gases in water. Let's take a look at like oxygen. Oxygen gets less and less as you increase temperature, and this is just kind of a big deal in terms of like if you have fish. Fish live in water and they breathe oxygen. The oxygen, and they, just like us, their gills breathe oxygen. Instead of extracting oxygen from air, they extract the oxygen from water. Now, so just to let you know, is that the oxygen that they're extracting is O2 that's been dissolved in water. So if you increase the temperature of your water, there'll be less and less oxygen in the water, and therefore the fish aren't going to live very well. For instance, trout ideally live in temperature of about 10 to like 13 degrees Celsius. So they need about this much oxygen, okay? About 0.005, okay? And my pen's going to do this wacky thing. So if you increase the temperature, the trout aren't going to not be able to breathe as well, and so they're going to migrate. And here's another example that I just talked about. All right, now the relationship between another relationship is between pressure and solubility and pressure. Concentration of gas in a liquid at any given temperature is directly proportional to the partial pressure of the gas. And it kind of goes, as you increase the pressure, the concentration of the gas will go up by some constant. So these two are proportional. So you could say C is proportional to P, and is proportional by some constant. This is when temperature is constant. Okay, this relation was determined by some guy named Henry. I don't know who he is. And so we call this Henry's law. And the K is Henry's law, and it's unique for each kind of gas at a given. Okay. This is only true at low concentration pressures, and where the gases don't react with the solvent, so there's no chemical reaction. There's another way you can rewrite this formula, and if you remember the gas equation from Chem 1, for instance, Boyle's law said that Charles' law said that the volume of a gas was related to the temperature of the gas, and with some constant, Charles' constant. Okay, we didn't use it in this form. We used it in this form, which we're going to do the same thing with Henry's law. Okay, so if you know, here's the initial concentration, initial pressure, final concentration, final pressure. And this just demonstrates Henry's law. Okay, as I said, here's the concentration of the gas, and here's the pressure. If you increase the pressure, you get more solubility. Now, why did this happen? It's basically because the pressure of the gas is forcing its way into the so if the gas pressure gets hard enough, strong enough, the forces will push itself into the solvent and be able to interact better. Okay, so this is what you get here is, as you increase the pressure, okay, the particles can move into the solvent better. All right, and so now let's apply Henry's law. The concentration of carbon dioxide in a soft drink has a partial pressure of about 5 atmospheres at 25 degrees C. The Henry law is constant for water. It is this value right here. So let's find the concentration of the CO2. We have K, which is this value here. We have the pressure, which is 5 atmospheres, and then we have so this is K. This is all one unit here. So this is the 3.12 is this value right here, and PCO2 is this pressure. Then you just simply do the math, and you get the concentration of carbon dioxide is 0.16 moles per liter. Okay, so now we're going to use the from the last problem, we found out that the initial concentration is 0.156, and what I want to know, what is the final concentration if you change the pressure from 4 times 10 to the minus 4th atmospheres to final pressure. The initial pressure is 5 atmospheres inside the bottle, and then when it's open, the final pressure is this. So this is final pressure, and the 5 atmospheres from the last problem is initial pressure. Okay, so this is 5. Okay, and this is 4.0 times 10 to the minus 4. and this value is 0.1516. So what is the final concentration after you release the pressure? Well, the concentration should go down, okay, because you're releasing pressure. And when you do the calculation, you can see that it has gone down. Okay, it was at 0.16, now it's at 1.2 times 10 to the 4th minus 4. So, this is one reason why your drinks, why they fizz out, okay, will get flat, is that when you open them up, is that the pressure inside the bottle can't hold the gas particles in as well, and they can escape. Okay, what is concentration dissolved nitrogen in a solution that is saturated into a 2.0 atmospheres? So what we're doing is we're using the initial equation here. We want to find concentration. We know K. We know our initial pressure. And then our final concentration of the nitrogen is this here. Okay, so this problem we're going to figure out this one. You have to think about it. So how many grams of oxygen gas at 1 atmosphere would dissolve in 10 liters of 25 degrees? So this is kind of a concentration. This says grams per liters. Okay, it turns out that what we want to do is we want to figure this concentration. So we want to find out how many grams per 10 liters. So we're going to be figuring out the grams per 10 liters. So we need to use our formula. Okay. And what it gives us is it gives us pressure, 1 atmosphere, and it gives us K, which is this value here. So first thing we're going to do is figure out this part right here using moles. And so we go K times P, which is this right here. And then, so we multiply the K times P and we get 0.0. This does it all in one step, but I'm going to talk about just 2 steps individually. So after you get done, this says that at 25 degrees, the amount of oxygen that would dissolve is 0.0013 moles per liter. Okay, now what we have to do is change this to grams. So multiply it by its molar mass. And then so multiply that by 32. And then also you want to find out, and that's in 10 liters, so you have to multiply this whole thing by 10. To get the grams, you get 0.416. Okay, so there's the answer. Or 0.42 sig figs, it's only 2 sig figs. This and this right here. This has 3, but remember you only go with 2. Okay, next problem is we're going to use the ratio of C1 over P1 equals C2 over P2. Okay. So solubility of water is approximately grams per liter when the temperature is 25 degrees. And the partial pressure gas is 760. So what we have here is the concentration C1 and initial pressure. And what we want to do is change pressure to 1,000 torr. And what happens to concentration? So simply just plug them in, solve for a new concentration, and you get this value right here. Does that make sense? So you're increasing the pressure, so the solubility should go up. And this is greater than this. Okay, solubility of polar versus nonpolar gases. Gas molecules with polar bonds are much more soluble in water than nonpolar. Okay, so that's because they form interactions. Okay, so here's just some examples of that. All right. They'll usually form hydrogen bonds with water or dipole-dipole. Also, some gases, when you put them in water, not only do they dissolve, but they will actually form chemical reactions. For instance, when you put carbon dioxide in water, it dissolves. Okay, so it floats around, and so it's dissolved in water. But also, what can happen is a chemical reaction where the carbon dioxide and water come together, form carbonic acid, and then that can actually turn into an acid-base reaction, and which is quite important in terms of what happens in like the ocean and etc. And here's another example. This is one reason why there's the acid rain. This is a gas that sulfur dioxide that often coal plants create. It can be dissolved in the water, but when it gets dissolved in water, some of these SO2 reacts with water, form sulfuric acid, and that sulfuric acid causes what we call is acid rain. Okay, and then we have this final one as well. Okay, when you open a bottle of some like pop or seltzer, okay, it fizzes. How should you store it to increase the time before it goes flat? Okay, so there's two ways you can do it. One is put it in the low temperature. The other one is put it at high pressure, or both. So, in one way you could do it at high pressure is, just keep it closed. Okay, that way no gas particles can escape, and it'll keep that pressure inside there. All right. Okay. Okay, the next part here is going to be we're going to be looking at ways of measuring solute in solvent in solutions. Okay, so the way that we have learned it in the past is something called molarity. Moles of solute per liter of solution. Okay, molarity varies with temperature. Volume varies with temperature. Solutions expand and contract when heated in solution. Molarity can change based on temperature. If temperature independent concentration is needed, we must use other units. Okay, so if we are just interested in the amount of solute and solvent, okay, then we can't use molarity, because if you increase the temperature of a solution, the molarity can change because the solution's volume can change. So there's other ways that we can measure concentration that are independent of temperature. Okay, the first one is percent concentration, also called percent mass or by mass or percent by weight. And it's percent by mass is equal to mass of the solute divided by the mass of the solution. Okay, so if you heat this up, this solution is still going to have the same amount of solute in solution times 100 to get in percent. And sometimes if you look at the side of a vinegar bottle or something, it'll have it written like this. And sometimes it doesn't even have this right here and just says this, 5%. And when you see that, it'll be weight to weight or mass mass. Okay, so let's just look at an example. What is the percent by mass of sodium chloride in a solution consisting of 12.5 grams of sodium chloride and 75 grams of water? Well, so it's solute over solution. Okay, so solute is 12.5. The solvent is 75. So add them together and then divide, and you simply come up 14.3. Right, let's look at another example. Seawater is typically 3.5% sea salt, and the density of seawater is 1.3 grams of solution per mil of solution. So actually, it's kind of important to write that down. This pen is doing a slidey thing. How many grams of sea salt will be needed to prepare enough seawater solution to fill a 62.5 liter aquarium? Okay, so how many grams will fit into this? Okay, what we know is this: 3.5 grams in 100 grams solution. The density is 1.03 grams solution per 1 mil of solution. And we also know that 1,000 mils is 1 liter. So let's see how we put that all together. Now pay attention to this because it takes some thinking. Okay, so density of solution is all right. And now another way of measuring concentration that's not dependent on temperature is something called molality, where you have it's moles of solute per kilogram of solvent, and so the amounts don't change. And so we're going to do an example of finding molarity and molality for the next couple problems. So pay attention to this. Again, like the previous problems, you're gonna have to think about it, and there'll be problems I'll give to you that'll be similar to these. So these will be good guidelines to help you figure them out. So what we have here, as I said, we want to find these two out: molality and molarity. And what we're given is 25.38 grams of iodine and 500 grams of carbon tetrachloride, and the density of that solution is 1.59 grams per mil. So here's everything we need to know. So what first thing we're going to do is find the molality. Okay, so what we have to do is figure out how many moles. So we divide 25.38 by the molar mass. Here's the molar mass. Okay, so here's the first step. And then we want to change this to kilograms, and that's this step right here. Okay, you can do it as all one, or you can do it in 2 steps. So you divide by the molar mass to get the number of moles, and then 500 grams is a half a kilogram. And so you end up when you do when you do the calculation, you end up getting 0.2000 molality. Now sig figs, you're not using the 1.59, you're using these two. So this has 4 sigs and this has 4 sig figs, so your answer will have 4 as well. Or you could write it as 2.000 times 10 to the minus first, little m. Or you could write it as moles I2 over kilograms of CCl4. Okay, now let's figure out molarity. Okay, now we're going to be using density in this case because density is in terms of solution. So density is 1.59 grams solution per mil solution. Okay, so we're going to use that information to help us figure this out. So let's go on the next slide to show you how I do it. So you have 25.38 grams of iodine and 500 grams of carbon tetrachloride, and the density is 1.59 grams solution for 1.00 mils per solution. So your solution is 525.38 grams. So how many mils is that? Okay, well, this relation up here tells you that for every 1.59 gram solution, there's 1 mil. And so what you're going to do is you're going to use this value and then actually divide it by the density. And you'll end up getting this. So, I mean, you could do this different ways. You could set up as a ratio. You could say 1.59 grams per solution per 1 mil has to equal 525.3 grams solution equals X mils of solution. And then you could come up with this. All right, different ways you can do it. And then you change it to liters, because we're finding molarity, which is going to be, so this is liters of solution. Now the moles, you just divide by the molar mass, you get 0.1. And then molarity is moles divided by liter solution. And here, now this has 3 sig figs, so the answer can only have 3. So we lose sig fig because the density. Okay, another problem here. This one is going to be going from percent solution to molarity and molality. We're going to do molarity first. And what we're going to do is assume that we have 100 grams of solution. Right. Now, using the density, I know for every 1.38 grams, there's 1 mil. So if I have 100 grams, how many mils is that? So what you can do is you can set up a proportion. 1.38 grams over 1 mil has to equal 100 grams over X. And when you do that, you come up with 72.5 mils of solution will hold 100 grams of HBr, which is the same thing as 0.75. That just should be 25 liters of solution. Okay, and then what we want to do is figure out how many moles is 40 grams. The molar mass of HBr you can figure out is 80.91 grams per mole. Divide 40 by that, you end up with 0.49 moles of HBr. And then you simply divide the moles by the amount of solution. This should be 2. And so the answer is actually 6.73, I believe, molar. Okay, now let's do molality. Okay, now molality. Okay, again, let's assume we have 100 grams of 40%. That means is that 40 grams of this 100 grams, 40 grams of it is HBr, and the other 60 is solvent. Okay, so we find out how many moles the HBr, again, is 0.49, and then figure out how many kilograms the solvent is. So 60 grams divided by 1,000 will give you 0.06 kilograms. And divide the 2 and you get 8.2 little m for molality. Okay, so there's a couple sets of problems to help you. I'm going to give you a worksheet where you can do a couple problems like this. Okay, more temperature independent concentration value. One is called mole fraction. Mole fraction is, let's say you have a substance that's made out of A and B, and what you want to do is find out how much of it is A and how much of it is B. And so let's say, so the mole fraction of A is going to be the amount of moles of A divided by the total moles of all of A plus B. Or you can do the mole percent, which is simply going to be this number up here. So let's say there's 0.3 moles of A and per one mole of components, then you multiply that by 100 and you get 30%. Okay, the next thing to go to is applying temperature independent properties. And one of those is called colligative properties. They're physical properties of solutions. They depend on the relative number of particles. Really don't depend a whole lot on the chemical who's in it. They can affect, one of the things they can affect how the vapor pressure. Okay, and so what we're going to do is look into some colligative properties. Okay, the first one's called Raoult's law. It says the vapor pressure of a solution equals the product of the mole fraction of a solvent, X solvent, and its vapor pressure when pure. P solvent applies for dilute solutions. So we have this formula here. So the vapor pressure of a solution is equal to the mole fraction times the vapor pressure of the solvent. Now, the why behind this is that what's going to happen is that, remember, a higher vapor pressure. So for instance, when you add a solute to your solvent, what that's going to do is it's going to decrease the the amount of solvent. Okay, so and that in terms of mole fraction. So when you have pure solvent, the mole fraction is 1 for the solvent. But if you add a solute to it, the mole fraction of solvent goes down. And notice this is that so if this becomes a fraction like 0.5 times the initial vapor pressure, the final vapor pressure will go down. So what we're doing is by actually decreasing the relative amount of solvent, we decrease its vapor pressure as well. And this just shows you how that happens. Okay, so the change of the vapor pressure is going to be related to the amount of solvent you add to it. Okay, it's solute. So the more solute you add to it, the vapor pressure is going to change. Okay. So let's look at an example here. So glycerin is a non-volatile electrolyte, so non-electrolyte. So what does that mean? Non-volatile means it doesn't evaporate very well. Okay, so we'll have a low vapor pressure. Okay, remember low vapor pressure means doesn't evaporate very well. Non-electrolyte means doesn't dissolve water. Okay, that well. I mean, doesn't split apart in water. Okay, so we don't really have to worry about that. And has a density of 1.9 grams of solution per 1 mil. 25. Okay, what is the vapor pressure? 25 degrees. If we add 500 grams of glycerin to 500 mils of water. Okay, so the vapor pressure per water is 23.8. So what's going to happen is, water's initial vapor pressure is 23.8 torr. So that means that 25 degrees, the water is supplying a pressure to the atmosphere by evaporation of 23.58 torr. Remember, torr is a unit of pressure. Okay, so what, in a sense, we're kind of diluting out the water by adding glycerin, and that's going to reduce its mole fraction and therefore reduce its vapor pressure. So what we got to do is figure out the mole fraction of the solvent. Okay, so first of all, we got to figure out how many moles of glycerin we have. We know there's 50 mils, and for every mil, there's 1.26 grams. That's the density. Okay, and then so this figures out how many grams. So this operation here figures out how many grams glycerin you have, and then you figure out moles. You divide by the molar mass. And so this is how many moles of glycerin have. Now, how many moles of water do you have? Well, the density of water is 1 gram per mil. So if you have 500 mils, it weighs 1 gram per mil, so it's 500. So this gives me 500 grams. And then figure out how many moles, divide by the molar mass, and you get 27.75. Okay, now to figure out the mole fraction of water, divided by moles, divided by the moles of the water and the glycerin. And that's this value here, and then multiply it by its original vapor pressure. And you can see that the vapor pressure goes down. And the reason why that does that is it breaks apart the hydrogen bonds. Okay, so let's move on. The vapor pressure of 2-methylhexane is 37.986 torr at 15 degrees C. You don't have to worry about the units, but 1 torr is the same thing as 760 millimeters per millimeters of mercury, or equals 1 atmosphere, which is normal atmospheric pressure. So, and you don't have to know that, but 37.986 is roughly 1/20th of atmospheric pressure. What would be the pressure of the mixture of 78.0 grams of 2-methylhexane and 15 grams of naphthalene, which is nearly non-volatile? So you notice here we're mixing a non-volatile into our solvent. Okay, so first thing we want to do, find out how many moles of naphthalene there are. So 15 grams divided by 128 decimolar mass of naphthalene. You can look it up. Figure out how many moles of methylhexane. Okay, again, and then this simple blah blah blah, and there you go. Okay, and this explains what's happening. Okay, so why non-volatile solutes lowers vapor pressure. Okay, lower vapor pressure, fewer solvent liquids in liquid, and has to do with the rates. Okay, now we're going to look at solutions that contain 2 or more volatile components. Okay, so in the last example we had a non-volatile in our solvent, but now what we're going to do is look at a mixture that has volatile. Okay, so that means they're going to dissolve. So if you take 2 substances that evaporate well, how are they going to affect each other's evaporation? Okay, so we go through this, and we'll end up coming up with the formula. And let me just show you how it all works out. Well, we take Raoult's of the 2, we use Dalton's law, and then we follow through. And what we end up is getting this, is that the total pressure equals the partial pressure of A plus B. And so it's going to be related to the vapor pressure of the substance is going to be dependent on the vapor pressure of A, vapor pressure of B, and how much of A and how much of B. So this is kind of a weighted average right here. Okay, so if XA is high, and if P and A were the same, and A was higher than B, then the the vapor pressure, total vapor pressure will be affected by A more than B. And so that's what this formula basically comes up with. So let's do an example. So let's say I have a mixture of benzene and toluene, which are both volatile, which means they evaporate readily. Then you have 1 mole of benzene and 2 moles of toluene. The vapor pressures of the pure substance are 75 and 22. What is total pressure of the solution? Okay, so figure out, first of all, the mole fractions. You don't have to do anything fancy. It's 0.3 and 0.67. Okay. And then now you can do it all in one step or 2 steps. So this breaks the last equation into 2 steps. First, you figure out the pressure of benzene, pressure of toluene, and then add them together. So 0.3 times 75, 0.67 times 22. And so the vapor pressure when you're done is 40. Okay, so if you look at it closely, you can see that it's somewhere between the two. All right. So if it was based totally on the vapor pressure of benzene, then benzene has a higher weight, but the amount of the toluene adds to that, and so you have to combine these two. Right, let's do another one. So here's 2-methylheptane, that same pressure, and so again, let's work through it. So take a look at it. You may want to write this down and try it yourself. Okay, so what do we have here? We have grams of methylheptane, grams of ethyl. So we're gonna have to change those to moles. We have vapor pressure of both of them. So we should be able to, and here's our formula. So we should be able to have molar mass. So first thing is figure out how many moles of methylheptane and ethylheptane. You get these two values. Figure out their mole fractions. Okay, and then multiply each one by their specific pressures, and we get 230 torr. Okay, now next thing is that so we saw that you could change the vapor pressure by adding things to a solvent. And now what we're going to do is what would happen when to freezing point, boiling point if we add solutes to a solvent. So freezing point of solution always lower than a pure solvent. So if you have salt water, the freezing points could be lower than water. If you have boiling point, it's always going to be higher. So if you have salt water, the boiling point of salt water is going to be higher, okay, than water. And the reason for this is because the molecular interactions are broken. For freezing, put salt in the water, it breaks apart the water. And it's not because of the sodium chloride, it's because the sodium and chloride break apart the hydrogen bonds of water, and it's harder for the the water to form hydrogen bonds, and so you need to decrease the temperature to cause the bonds to hydrogen bonds to form better. Okay. So what you'll see is a change of temperature boiling, and it's going to depend on how much of the solvent and solution you have. We'll see how that works. And we have two different. If we look at the increase in the temperature of boiling point when we add a solute, or we look at the decrease. So one is called elevation, one is called depression. Okay, freezing point depression. this. Symbolized by delta TF. So delta TF is equal to some K, which is dependent on the solvent and then the molality. Okay. So delta F is the final temperature minus the initial temperature of the freezing point. So the final freezing point minus the initial freezing point. M is the molality and Kf is the molal freezing point. And we can write a similar equation for boiling point elevation. Okay, here's a look at the different ways of measuring concentration and how they relate to if they're temperature dependent. Molarity is temperature dependent, and percent by mass volume is our temperature dependent. And that's because the solution, both of these in terms of solution. Okay. All right, let's move on. All right, estimate the freezing point of a permanent type of antifreeze solution made up 100 grams of ethylene glycol, molar mass this, and 100 grams of water. So what we're doing is we're putting 100 grams of ethylene and dissolving it in 100 grams of water, and what happens to the boiling point of water. So first thing we have to do is figure out the molality of our solute. Okay, so we have 100 grams and divide by 62 point, you get 1.611 grams of ethylene glycol. Okay, next thing you want to do is figure out the mole. That's the moles, and the molality is moles solute per gram solvent. 100 grams is the same thing as 0.1 kilograms, so this is the molality. Right, so the change in temperature is use the K for water as 1.8, and you'd have to look this up. 1.86 Celsius per molal time, and then times the molarity, which is 16.11 molal. And so there's a change in 30.0 degrees Celsius, and this would be minus, okay, because well, actually we will apply it down here. So what is the final freezing point? Well, the initial freezing point of water is 0 degrees. The change is sorry. So here's our change, okay? Here's our initial and here's our final. And just plug it in, and so you get minus 30 degrees Celsius. Okay, ethylene glycol is what's found in antifreeze, right? And so that's one reason why antifreeze is why you put ethylene glycol in your radiator, so it reduces the freezing point of water, so you don't have a cracked block when it gets cold up. All right, so let's do this problem. So 0.25 grams of unknown organic compound is added to 25 grams of cyclohexane. So this problem, what we're going to do is be figuring out molar mass using freezing point depression information, and actually be doing a lab like this. And so and what happens when you add the two? The freezing point drops to 1.6. And we know the Kf of cyclohexane is 20.2 Celsius per molality. So let's go through how you would figure out the molar mass. First of all, the formula is for freezing depression is this right here. So so it goes down by 1.6 Celsius. That this is the KF, okay? It says Celsius per molality. I changed molality to moles per kilogram. And we don't know the molality of our unknown, okay? We know how many grams, but that's what we're going to figure out, right? So so simply what we do now is what we do is solve for x, this part right here. And sorry, this should be x moles per 0.025 kilograms right here. Okay, I left that out. So what we do is we are going to solve for this part right here. So just multiply both sides by 20.2. And when we do that, we get x moles per kilogram per 0.025 kilograms. Where'd I get the 0.25 kilograms? That's 25 grams. Is equal to 1.6 divided by 20.2 moles per kilogram. So you can see the units work out. So now what we do is solve for x, and we get 0.00198 moles. And we know we say molar mass is grams per mole. So we have the amount of grams of our unknown divided by the moles of unknown. So grams divided mole is our molar mass. Now in terms of significant figures, you have 2 here, 3 here, and 3 here, and 2 here. So your answer should only have 2. So the answer really should be 100 or 30, or where the 0 is insignificant, 1.3 times 10 to the second grams per mole. Okay. Let's do another problem, this time using boiling point again to find molar mass. And so you can see that not only can you figure out how temperature changes and etc., you can use it to figure out something pretty cool, molar mass. So you can figure out indirectly, you can figure out molar mass. So we're going to see it again that we can figure out using osmosis, osmotic pressure. Okay, so we have this problem. You have 2 grams of unknown sample, dissolved in 15 grams of carbon tetrachloride, and a boiling point was determined to be 77.85, so it went up. So we need to find the molar mass of that, and so we're given the K, B, and the original boiling point of our carbon tetrachloride. So our formula is change temperature equals K times M. So change temperature is 1.35. So 1.35 has to equal to K. So it's 5.07 Celsius per mole per kilogram. So I changed molality to moles per kilogram times X moles of our unknown divided by the 15 grams, which is 0.015 kilograms. Okay, so what I'm going to do is I'm going to solve for this here. So multiply both sides by 5.7, and I end up getting X moles equals 0.266 moles per kilogram, which is 0.00399 moles. So that's how many moles of unknown I have. Okay, the molar mass is going to be the 2 grams divided by its moles, and the comes out to 500.7 grams per mole. And our sig figs are 3, 4, 3, 3. So we should go with 3. So it's going to be I guess it could be 5.01 times 10 to the second grams per mole. All right, next problem here. So Sierra. Antifreeze literature, freezing point 40-60 solution Sierra antifreeze in water is negative 44 degrees Fahrenheit. What is the molality of solution? Okay, first thing is that our formula, okay, K is going to be in terms of Celsius. So what we do is we have to change the Celsius. So we just use the conversion and we come up with the change in temperature is minus 20. So minus 20, because 0 degrees, so 0 degrees is our initial solution, minus 20 is our final, so the change in temperature is minus 20. And sorry, that minus shouldn't be here when you put that in. Okay, so we have this, so equals x molality. Let's kind of swap this equation here, and then solve for x. And so xm equals 20 divided by 1.86. Again, discard the minus because we know molality is not negative, and you end up with 11 molality. All right. Technically, because this is just one significant digit, this really should just be 10, or 1 times 10 to 1 times 10 to the first molal. Okay, so now let's expand on it. In the previous example, 100 mils is known to have 42 grams of the antifreeze and 60 grams of water. And so what is the molar mass of the compound found in the antifreeze? So what is the molar mass of this 42 grams? We're going to use the last problem's information where we found the molality is 11 molal. So 11 molal, it means 11 moles per 1 kilograms of solvent. We don't know how many moles of our substance we have. We know how many grams it is, but we don't know how many moles. And we know the kilograms of the water is 60 grams or 0.06 kilograms. So the amount of moles, so just so solve for x. Okay, so multiply both sides by 0.06 and you get x moles equals 0.66 moles. And then the molar mass is going to be the 42 grams divided by the 0.66 moles, and you get 64 grams. Again, technically it should only be one significant digit, so it should be 60 or 6 times 10 to the second grams per mole. Okay, so here's extrapolation problem that we're going to use that's going to relate also to osmotic pressure in a little bit. If all the following generic compounds have the same Kb, which will cause a greater change in the boiling point at 0.25 molality? Okay, so because so each one of these is a non-electrolyte, like we're saying. And really doesn't matter, okay? So to a general degree, we're saying is that it doesn't matter what the substance is that you dissolve in your solvent. It's how much of it that you dissolve. Now, it turns out that all of these are at 0.25 molar. So there's 0.25 molar of MX, 0.25 molar of MX2, and so forth. Now, which one of these is going to generate the most particles is the one that's going to generate the biggest change in the boiling point or freezing point. So this will break into 2 parts, M and X. This will be broken into 3 parts, MX and 2 X's. This will be broken up into 5 parts, and this will be broken up into 4 points. So C is going to break up into the most parts, and it's going to have a greatest effect on changing the boiling point or freezing point, independent of what they are to a certain degree. Ta-da! All right, next thing is we're going to get into osmotic pressure. So first thing we want to do is we're going to talk about membranes and permeability. Membranes separate, we're going to think in terms of particles in a solutions from each other. For instance, as examples, cell walls are membranes. So cell walls let in, well, one side has particles on it, and the other side has particles in it. and they're separated by the cell wall. Now, if it was a impermeable membrane, then nothing could pass through. But semi-permeable means some of the particles could move through and through depending maybe on size or other things like the electrical ionic ability and so forth. All right. So degree on permeability depends on the type of membrane. Some pass only water, some pass water and small ions, and so forth. Okay. So osmotic membrane, semi-permeable membrane that lets only solvent molecules through. Okay, so if you have two sides, you have X and Y, and our solvent is going to be water. We're going to say, okay, and so osmotic pressure will only let water through either side. It won't let any other particles. So we might have a bunch of sodium over here and a lot of potassium over here. The only thing that's going to move is the water. And that's going to be important, okay? So now the water can move from one side to the other. Now what's going to happen is water is always going to move to the side that has less relative water. So that means, let's say you have on this side you have there's 2 molar sodium chloride, and over here is 4 molar sodium chloride. Okay. Now so what that means is it's relatively there's less water over here. Okay. And there's more water over here because this side is more diluted, right? And so what's going to happen is water is going to move from the more diluted side to the more undiluted side to try to bring this 4 down to 2. Okay. So that's what happens. So that's what's going to happen. For instance, if this side has a lot of our solute in it, what it's going to do is water is going to move into it, and that water is going to cause this guy to actually expand, okay? Because more water is going into it. So the more the water goes from less concentrated to more concentrated. So the water goes from dilute to more concentration. And that's to balance out the concentrations. Now, when it does that, okay, what it does is it causes, like I said, it causes, so if this inside, or let's say the inside is more concentrated than the outside, the water is going to go and it's going to cause it to expand. And if you don't let it expand, okay, say this is we hold it, what's going to do, it's going to cause, if you have a piston here, it's going to add pressure onto this piston, and it's going to cause this piston to move up. And what we can do is we can measure how much pressure is being added to this tube from this movement of water from dilute to concentrated. Okay, so how much pressure do we have to add to keep it at the same volume? Right, and so there's actually a formula for that. So the osmotic pressure is going to look just like the ideal gas law. The ideal gas law said PV equals nRT. This is going to be, instead of using P, it's going to be osmotic pressure instead of atmospheric pressure or just gas pressure. And so here's our information. And you could also write it as this, where M is moles per volume. Okay, so if you divide both sides by V, you'll get molarity. Okay. And we'll use it in both forms. But typically right now we're going to be using it in this form. Again, you can think about it. It's what happens with different solutions. So isotonic, that means if both, if your solutions are of the same amount of, 4 and 4, there will be no movement. And so we say it's isotonic, and so there's no movement of water. Hypertonic is where higher concentration on the outside than inside. So let's say that this is the outside and the inside, and let's say this is 4 and this is 2. What's going to happen is this side, the water is going to move, all right? Okay, and so this is actually going to shrink. So hypertonic, so cells, so if the outside of the cells have more salts in it, the cells will shrink or dehydrate. Okay, and that's like if you eat a lot of salt, okay, and a lot of salt goes in your blood, the blood is going to it's going to pull water from your cells into your blood, and your cells are going to become dehydrated. Okay, now a solution that's hypo, which means under solution. So the outside, hypo means less. So if the outside is lower than the inside, what's going to happen is go in and cause the cells to expand and possibly even burst. Okay. So let's use a problem, use the osmotic pressure. So eye drops must be the same osmotic pressure as human eye to prevent water from moving in and to and out of the eye. On commercial eye drop solution is 0.327 molarity. What is the osmotic pressure in the human eye at 25 degrees C? Right, so what we're doing here is solving for P. We have this. Okay, with molarity, we have we have R, which is the universal gas constant, and we have to change temperature to Kelvin, and then simply solve, and it's 8 atmospheres. Okay, now what we're going to do is use this to figure out molar mass, okay? Right, osmotic pressure of aqueous solution of certain protein was measured to determine its molar mass. And I used to do this when I was working in biochemistry lab years ago. So let's say you take 3.5 milligrams of a protein. Now, knowing the molar mass of a protein is really important, and it's hard to do. You just can't take it out and weigh it, okay? And so this is a cool technique to do it. You could use freezing point depression as well, or boiling point elevation. But here's another way of doing it. So you have 3.5 milligrams. That's your unknown. And it forms 5 ml solution. Okay, the measured pressure is 1.54 torr at 25 degrees C. Calculate the molar mass. So what we're going to do is we need to find out how many moles 3.5 3.5 milligrams. And there's different ways to do this. So we're going to use our formula. So we're going to solve for molarity, because molarity is moles per liter. Moles per liter. Okay, and so our pressure is 1.54. We want to get that in terms of atmospheres because that's what we use for R. So the relationship between atmospheres is 1 over 760. Do that, and you figure out. So you figure out how many atmospheres. And then the bottom 0.0286, 206, 298. So do the math, and you get 8.28 times 10 to the minus fifth moles per liter. Okay, so you know that X moles per liter has to equal 8.28 times 10 to the minus fifth moles per liter. All right, your liters is 5 milliliters, which is, so multiply both sides by, so multiply this side and this side by 5 milliliters, which is 5.00 times 10 to the minus third liters. And you end up with 4.14 times 10 to the minus seventh moles. Then the molar mass is milligrams. So getting that terms of grams. And then the moles, divide them, and you come up with this. Let's check the, now really, we could make this 25.0. And it's, so you have 3 sig figs. So 3 sig figs. Okay, here's another problem. Solution of 5% dextrose, C6H1206. Glucose, another name for glucose is dextrose. In water placed into an osmometer, shown at right, has a density of 1 gram per mil. The surroundings are filled with distilled water. What is the expected osmotic pressure at 25 degrees C? Now, what we're going to do is use this formula here, so we have to figure out molarity. Now, we had a problem in the previous slide where you were able to go from percent mass to molarity. So that's what we're going to do here, and then we're going to use this formula. So what we're going to do is assume we have a 100 gram solution. And that 100 gram solution, 5 grams of it is 5 grams of the total solution is of 100 grams is dextrose. So if you have a 100 gram solution, how many moles of dextrose is that? So there's 5 grams per 100 solution. So you divide the 5. The molar mass is 180, so divide the 5 grams by 180, and you get 0.0278 moles of dextrose. Okay, now we're going to use density to figure out what is my volume of my solution. Well, my mass of my solution is 100 grams, and my density says for every gram, 1 gram, it has a volume of 1 mil. So simply, you can do the math, or you can just do it in your head almost, is that 100 gram solution, and then solve for mils, you'll get 100 grams of solution is 100 mils of solution, and this should be, all these should be 100.0. So the molarity is going to be the moles divided by the volume, and it turns out to be 0.278 molarity. Okay, 5% is our significant digits, so we can only have, so it's 0.3 molar. So plug everything, 0.3 molar and moles per liter times the universal gas constant times the temperature, and you end up get 7 atmospheres. Here's your answer. For a typical blood plasma, the osmotic pressure at body temperature is 5,409 milligrams of mercury. The dominant solute is serum protein. What is the concentration of the serum protein? Okay, we use this formula. We have to have, we want pressure in terms of atmospheres. So we can use this as our R. So here's the relationship of atmosphere millimeters, and so you end up getting 7.17 atmospheres equals the molarity times R times T. Okay, T is 37 plus 273. Okay, and then solve for molarity, and you get 0.280 molarity. Okay, now this problem is kind of similar to what we talked about in terms of boiling point and number of particles. Which aqueous solution has the highest osmotic pressure? Well, the solution that has the most particles is the one that's going to have the highest osmotic pressure. So, in a similar problem we talked in a few slides ago, is that you have to count the number of particles. So this has 4 particles, but we also have to include the molarity. So the overall molarity of the number of particles would be 0.1 times 1, 2, 3, 4, or 0.4. For this guy, this would break into 3 parts, a BA and 2 nitrates, and its molar is 0.15, so it's 0.45. For this one, it breaks into 3 parts, 1, 2, 3. Has molar of 1.1, so it's 0.3. This guy could break into 2 parts, N and NaCl, and it's 0.15. So this is 0.3. Made a little mistake there. And the last one, this guy does not break apart at all, so it's going to be 0.2 times 1, or 0.2. So B is going to break into most parts, and it's going to cause the highest osmotic pressure. And this relates to it is that when you put sodium chloride in water, if you just assume that sodium chloride is just one particle, then it behaves according to the equation that we have. But when you do that, it turns out that the actual freezing point isn't what you expect to be. It's almost twice as high as it is, and that's because the particles, it breaks into 2 particles, and each particle is going to affect the freezing point. Okay. For instance, and it relates to this is that if you buy salt at the store to help your driveway from or sidewalk from freezing, you could buy regular rock salt, which is NaCl, or you can buy, sometimes I think it's called heat, and that's calcium chloride. And calcium chloride breaks into 3 parts instead of 2, and so this even if these guys, the calcium chloride and the sodium chloride, aren't the same molality, the calcium chloride is going to be better. It's going to lower the freezing point more because there's more particles. And here's a calculation to figure out what's going on there. And then, all right, we're going to wrap this up. The colligative properties are dependent on how many, what's the amount of particles, not necessarily their chemistry. Though in the last part, we saw that is that it matters sometimes who we dissolve. It changes freezing point and boiling point, etc. But we have different things that we used before. We had Raoult's law, freezing point, depression, boiling point, elevation, and osmotic pressure. All are determined by the number of particles. This I here, okay, this I is related to, in the previous, it tells us how many particles it broke, the substance can break into. For instance, like sodium chloride, and they're experimental values, but they're really close to the number of particles. For instance, sodium chloride, um, I don't know what its I is. You can look it up, but the I is going to be pretty close to 2. Okay, and so typically when we do these problems that we've done, we don't include I because we're assuming all these substances have the molality is the only thing that affects the change. Okay, but technically we should include, this is called the Van 't Hoff constant for its substance, and we're not gonna get into that. Okay, so but these are the equations that we use. Now we've been talking about homogeneous mixtures, and we'll just briefly cover heterogeneous mixtures. Okay, just to give you an idea what you look out for, and I'll give you one slide, and you just kind of go, okay, don't need to know anything about it. People spend their whole lives working on these things. Okay, so it's kind of a shame that you can't spend more and more time on it. But just give you heterogeneous mixtures. Remember, mixtures that you can see the separation, that they're not uniform throughout. So it'd be like sand and water, oil and water, so forth. There are 2 or more phases that are not homogeneous. There's 2 major types, and one type is suspensions, large particles mixed in a solvent. Okay, in 2 phases. That'd be like oil and water, or you might, I don't know. It's like if you had, I'm thinking about. Sometimes I've bought beer and hazy beer, and when you look at hazy beer, what makes it hazy is because there's fairly large hop particles that are floating around in it, and so it's kind of, so the hops are suspended. And then there's things called colloidal dispersions, and those are very, very small particles. Sometimes you can't even see them, and they look like true solutions. But one way you can tell if they're not is that what you can do is you can fire light. So if you have a solution that's colloidal, so this is like a test tube, and sorry, it's doing all this zigzaggy thing. But if it's so if you look at it, it looks like it's clear all the way through. But if you fire like a laser at it, what it's gonna do is it's gonna scatter or diffract or refract that light. And so there's experiments that do that all the time. Okay, so so this finished up this material. It's chapter 12. I will send out worksheet that will go over these problems, that especially the Raoults, Henry's, changing percent to molality and molarity, doing osmotic pressure and doing freezing point depression. And hopefully there'll be a good selection of practice problems. And then the next test, there'll probably be 2 parts. There'll be a multiple choice, and also be a working set of problems that you'll have to send in me your answers and your work. Okay, so I'll give you more information on announcements about this one.